McGill, talking about dynamics of planetary atmospheres.
Okay, cool. Well, thanks, guys. Thanks for having me in your new room. Sounds. So I hope you guys can all see this. I have to look down on my work now, but anyway, I'd like to talk about the dynamics of planetary atmospheres and in particular hot Jupiters, or close-in Pegasus planets, as they're also called. Basically, Jupiter-like planets close in to their host stars. So, so just a brief outline. That work? Yeah. Just a brief outline. Basically, I want to start off talking a little bit about observations. Sorry for those of you who are aficionados in the field, but I'll talk a little bit about the current state. It's progressing very rapidly, so it's always a good idea to keep updating where we are. But I really want to concentrate on these last two issues, which are phase curve and spectra, which are coming out now in prodigious numbers, and really are allowing us to start constraining the dynamical models. And then I'll go into what exactly the dynamics entails, the various methodologies that people use. It basically breaks down to two components, the hydro part and the radiation part. And so I'll try to explain both of those and what is being done in the field with those. Finally, move on to the results, and then if we have time, I'll talk about where we're going with this and what the next plans are. So as of Friday, there were 260 planets announced in 224 systems, with 25 of those systems having 2 or more planets in them. And they run the gauntlet in all the orbital parameters. Here I've plotted eccentricity, semi-major axis, or mass versus semi-major axis. And again, I'm not really going to dwell on the overall characteristics of the planetary ensemble as a whole, but really want to just draw your attention down to these close-in guys down here that orbit their stars every, say, 3 days or so. Another thing I wanted to point out is that these, the low there seems to be a decreasing envelope of eccentricity as you move closer into the host star, and it's pretty widely believed, with a couple notable exceptions, that all the planets that are close in are tidally circularized, and their orbits are synchronized with their spins, so that one side of the planet always faces their host star. So of these, a fraction of them have orbital inclinations that are favorable for transits, both primary transits and secondary transits. And so here's just a schematic of this. In this diagram, the observer's up here at the top of the page. This particular one is diagrammed to be an eccentric planet. I don't know why I picked that, but anyway, as the planet passes in front of the star, you get a blocking of the stellar light, and then you can see the converse effect where the star actually eclipses the planet, and they're starting to be observed, quite a number of these observed, and these are typically observed in the IR, where the planetary flux becomes such that you can actually see it, in contrast to the stellar flux. This is an example in 8 microns. This is just a diagram of 8 micron as a function of phase. It doesn't have this down here. And you can see these two eclipses occurring pretty distinctly. So among those, 260 planets, about 30 so planets actually do transit their stars. And it's just not meant to read any of this. It's just meant to show that there are quite a few of them out there. They're all short period. They're all massive, with the exception of they're all quite massive, yeah. Neptune's not transiting. No, yes, they're all quite massive. So you can do all kinds of things with transiting planets that you can't do with normal radial velocity planets. And just to name a few of them, one is that it was suggested early on that these planets are so close into their stars that you should be able to drive a dramatic wind, off the surface of the planet and actually evaporate the planet. And there were suggestions for HD 209458 that this was actually happening. You looked at the size or the eclipse radius in sodium, and you saw that it was actually exceeding the Roche lobe of the planet. However, I guess subsequent work has suggested this may not be happening for that particular planet, but it still remains a viable thing that could occur in some systems, maybe in younger systems as well. And even if it's not necessarily something that affects the overall evolution of the, maybe it's not dramatic enough to affect the overall evolution of the planet, it may play a big role in mixing various chemical species up high into the atmosphere. Just another thing to pull out would be an example of the Rosler-McLaughlin effect, which is as the planet crosses the disk of the star, you preferentially block, if the spin is in this direction, you preferentially block blue-shifted or red-shifted light. And so you can see this little wiggle in the radial velocity curve. And from that, you can deduce the relative spin axis of the planet and the orbital axis of the planet and the spin axis of the star, and look at the relative angle between the two. And so far, to my knowledge, that this particular example, I believe it was HD 209458, this particular example showed very good alignment, that as you would expect naively, the orbital plane of the orbital plane is perpendicular to the stellar spin axis. Which makes modeling a little bit easier because the hotspot remains fixed in one location. So perhaps more interesting to me, at least, is the overall evolution of the planet and how the proximity of the host star plays a role in changing how planets evolve. And so here's of the transiting planets, you of course can get rid of the m sin I degeneracy in the radial velocity curves, and you can also get a radius as long as you know a stellar radius to some accuracy. And so you can start looking at average densities and start comparing these to evolutionary models and whatnot. And the thing to take away is that there's a huge diversity in this class of planets. There are planets that are too large to be explained by models, and there's planets that are actually too small to be explained by models. So we still don't have a handle on exactly whether or not this is an effect of the host star or how the overall evolution lands you in various locations in this diagram. But this is all very interesting questions that we can begin to start addressing with transit observations in particular. So I mentioned the overall evolution of the interior. We, of course, know a lot about Saturn and Jupiter, which are our analogs to these planets, although they are nowhere in the correct, obviously in the correct irradiation regime. But this is an example of the models that have been formed for Jupiter and Saturn. And most of these constraints come from, I believe, Voyager flybys, looking at gravitational moments and such things, and fitting them to models. And basically, these planets have some sort of rocky core of various sizes. Saturn has probably a much larger rocky core than Jupiter, say 20 Earth masses, while Jupiter has something up to 10 Earth masses of a core. And then it's surrounded by a hydrogen-helium envelope, metallic, and then moving on to molecular in the outer regions. And this is exactly that. This is just for different equations of state constraining the sizes of the core for Saturn and for Jupiter. But the point here is that Jupiter and Saturn are fully convective. But if you take Jupiter and Saturn, you place them next to your host star, what happens is that you no longer have a fully convective atmosphere. You have an isothermal region develops on the outer edge. And the question for the overall evolution of the planet is, what is the effect of this isothermal region on the evolution of the radius, the evolution of the internal entropy, et cetera? And so as an example of this, this was a paper by Brose et al. That these are one-dimensional evolutionary models. So this is age in gigayears down here. And these are at different locations. So these are, I don't know if you guys, can you guys read this from the Mac? The solid line is a 0.3 Jupiter mass, and then the dotted lines are, the dashed lines are a Jupiter mass. And then these are varying distances from the host star. So this red one is the closest, and I believe that they put that at 0.02 AU. So there's a range of 0.02 to 0.06 AU. But again, the point is that the irradiation retards the contraction of the planet. And so you end up with a larger radius than you would otherwise. And so this irradiation, again, is feeding back into the overall evolution of the planet, and it's not quite clear how. These are one-dimensional models, and so you're modeling the subsolar point, the point that's facing directly to the star. So the degree of redistribution and of heat to the backside plays a big role in the actual effect of this.
So the ones the red ones, is that one only 0.2 Jupiter mass?
This solid one is, it's a small, very small, but it's very close. It's 0.02 AU.
What's the biggest size of the Jupiter mass?
Observationally,
No.
in the models, I can't read. Yeah. So this is 1.3. So maybe right here. Yeah. So, but obviously this isn't the whole story because you have this huge diversity in the planets. It's not. If this was the whole story, you'd expect. I don't have. This is a function of semi-major axis, but you'd expect all the guys at the same semi-major axis to have the same radius, but they don't for a given mass. Sorry, what? And a given age. Yes, we're right. So I'm implicitly assuming that these are all the same age, but that's a good point. Okay, so the other set of observations that have been coming out are spectra and phase curves. And for the most part, I think there's a lot of data coming out on this right now, but I'm going to concentrate on the two big shots, which are HT 209458 and then 187933b, which is actually, I think, the most promising because it's got the best star to planet flux ratio that we have. So anyway, phase curves, basically you take Spitzer and you stare at it for some duration of the entire orbit, and you see how the flux changes as a function of time. And so this is an example of 209458 by Cowan et al. in the 8 micron band. And so just look at this top panel here. The argument is that, their conclusion is that the energy is redistributed very efficiently, or at least 30% of the energy incident on the day side is distributed to the night side. So this is the flux normalized by some mean flux as a function of phase. So this is 0 to 2 pi. So you can see it's fairly consistent with a uniformly heated or uniform temperature body. And so this is in stark contrast to an object like Upsilon Andromeda B, which in 24 microns shows this what the authors claim is a fairly large day-night temperature difference between the two hemispheres. This. That's a good question. I don't know. Oh, they do. Yes, for sure. I mean, these are two different instruments. I'm not actually. I don't know too much about the observations. I'm sorry. Errors. Yes. Again, 189733b is a very, very nice object. It's a fairly small star, a fairly bright planet. So several phase curves have been done for this object as well. This one done by Knudsen et al. And this is a nice picture, but really you need to concentrate on this line here. This part's made up. But this is the brightness is a function of phase. This would be the point directly facing the planet. So again, the idea is that the planet is locked to the star, and so as it rotates, you're seeing different fractions of the night side and the day side. So you can pull out what the temperature would be along some sort of hemispherically average temperature as a function of phase. So they do this and then tie it to some models and pull out a temperature difference of, say, 230 degrees in this instance. And this was in the 8 micron band. Now, they've also come recently, just within the last week or so, come back and done it again in the 24 micron band. And as you would expect, you're seeing different regions of the atmosphere, basically different heights in the atmosphere in different wave bands. So here's an example of pressure versus wavelength. This is the pressure at which the photosphere exists for that given wavelength. And so if you're looking at 24 microns, you're over here somewhere, and 8 microns, you're down here. So you can see you're basically probing with this assumption of what the opacity is in the atmosphere. You are probing different regions in the atmosphere by looking at different regions in the spectra. So there's two things to note about this diagram. And the first is the location of the hottest spot. And so you can see that is actually, it's not facing the star. And so it appears that this hotspot has been advected downwind to some degree. And this was evident in both the 24 micron and in the 8 micron. In fact, the 24 was advected further over. The second point to note is the location of the minimum in this curve. Now, you have to take this with a little bit of a grain of salt, because that region right there, well, the box shouldn't be quite there. I think it should be right here. This region wasn't probed. It was only they only monitored a fraction of the orbit, and they had originally claimed that they had seen the global minimum, but I think that they are now convinced that they didn't necessarily see a global minimum. But if we took their measurement at face value, you see that the hot spot, or the coldest spot, is actually on the day side of the terminator, which is the 90-degree point, and that's quite an odd feature that no one understands at all. And so I'll come back to that later. But these are great measurements, but I think if we need to fill that in to be able to say that definitively. Okay, so spectra are taken in two manner. The most popular, or first done, was differential or transit spectroscopy. So you basically monitor the transit in a range of wavelengths, and then from that you extract a spectrum of the planet. And so the first such model of 209458 was done by Swain et al. And you can see that's the green data points here. And overplotted are various black bodies of various temperatures, 17, 1250, and there's 800. And then this brownish line is a model. I believe it's a Burroughs model. So from this observation, the group claimed there were very little features. There were very little features in the spectrum, and it's somewhat consistent with some sort of thermal emission. And you'd expect there to be a lot of features from water and such things as that, but you don't see any of this. And so the conclusion was there's either clouds or something is smoothing this out, and we're seeing a very flat spectrum. More recent measurements by Knudsen et al. have come back to the same object and now have quite a bit of features, quite a few features in their spectrum. And I've actually been trying to figure out exactly what the difference in the measurements were. But again, there's two different instruments. But why exactly, I'm not quite clear why they got a different measurement than the Swain-Hall group. But anyway, the point is the data shown in the circles here shows quite a bit of variation. This feature here is actually water, and then you move on. Here's the 24 micron. The dotted areas down here are the Spitzer band passes. Now, the model here shows clear deviation from this water feature here. So in the models, you'd expect a water absorption in this whole region in here. But in fact, you're seeing water in emission. And so recently, this has led to the suggestion that to interpret this, you need to have a temperature inversion in the upper atmosphere. That is, it needs to get hotter. There needs to be some sort of stratosphere in the upper atmosphere of the Jupiters. And I'll come back to this a little bit later. This is not too unexpected, in fact, but it was a surprise for the modelers when these guys did this. The other way that this is done spectras are done, is to look in the, this is done with Hubble, this is 3,000 to 7,000 angstroms, is to look at the transit radii in various wavelengths. And you can see, again, there's quite a bit of features here. I believe it's a methane feature here. And this is a percent absorption depth. And so you're seeing various features from absorption. But again, you're seeing them in this. Again, you're seeing down here, the important point is that you're seeing a temperature inversion.
Sorry, what was the Swain-Hall data? What's that?
This is IRAS. No, IRS. It's on Spitzer.
Okay.
And I think it has a resolution of 0.25 microns. Is that right?
And the wavelength range, because that
sorry, I can't.
spectrum is very narrow. So.
This guy here. Yes, this is encompassing this is 14 to, well, their data goes from 8 to 14. So that's just in this region here, where you still would expect to see some sort of a ramp up if the models were.
Considering how noisy that data is, it's not that much of a discrepancy.
Yeah, and the other explanation that some dynamical modelers would put forth is there are features that are time dependent, but we'll get to that later. But yes, that's a good point. So again, just to finish up with the spectra, for 1897333b, similar measurements were taken, and this time you don't see this inversion. And so here's another object that's reinforcing this idea that this is a very diverse class of objects. You have some objects that have inversions and some objects that don't. And again, then this is with the Hubble. Now you're seeing a very uniform region. So the red points are the observed region. And so these authors suggest there's some sort of a haze that's causing this kind of a very uniform emission. No features whatsoever in this shorter wavelength region. Okay, so the idea is, can we use all those to start constraining dynamical models and figure out what's happening on the surface of these? And then ultimately, the goal is, of course, to tie it into the overall evolution of the planet. So to do this, really you need hydrodynamics, and you need radiation transfer of some sort. And ideally, you'd have some sort of three-dimensional radiative transfer code that included all your, detailed fluxes as a function of wavelength, and et cetera, but this is, of course, computationally unfeasible. So various approximations have been undertaken, and really, they fall into two classes: your choice of dynamical method and your choice of radiative transfer. So there are, I would say, three major ways of approaching this problem. This is what are known as the equivalent barotropic equations, which are two-dimensional equations. And I'll get a little bit more into depth in each one of these as we go. But just again, to give an overview. The second are shallow water, which are approximately 3D. And the final is to solve the full Navier-Stokes equations. For the radiative transfer side of things, the group the methods people have used are relaxation methods, kind of a Newtonian relaxation, or what's known as flux-limited diffusion. And this final thing is, if we have time to talk about what the future is holds in store for me, at least, I'll talk about that a little bit more. So equivalent barotropic, they said they're 2D. So these are latitude and longitude grids on the surface of planets, and so you're neglecting you're averaging over the radial extent, and basically you solve some sort of two-dimensional momentum equation. Here, h is basically the scale height, so this is your pressure force, some sort of Coriolis force. You can include a viscous torque here. And then your energy equation is basically an evolution of your scale height. And then there's this term here, which is your radiative forcing. And so I'll get back to here, but basically this is the form of the equation. This is a slightly different formulation. It amounts to somewhat the same thing, although they do include the compressibility in their equations. And so this top plot here is James Cho et al. Collaborators who have done these type of simulations. This is the temperature as a function of location on the grid for various orbits. And again, it comes back to this. We're looking at the same location on the planet, and so we're seeing time-dependent features.
How much of the radius is being simulated here? Is just some outer shell?
So these are two-dimensional. So they're neglecting radius entirely. One zone.
They mean they want to go all the way to the center of the planet?
Oh, no. It's supposed to be, it averages over several hundred kilometers. Yeah, so it's an outer shell. It's basically, at least the 3D models, it's a little bit hard to say exactly how to do it in these two-dimensional models, but in the 3D models, you want to reach into the interior adiabat. And once you're on the interior adiabat, then you can say, okay, that's my bottom boundary condition. But the overall features of these models are very uniform temperature distributions, and also these features that come and go, these time-dependent features. The second of the three types of ways of solving these are what are known as the primitive equations. They're used quite often in Earth's atmosphere, actually. Yeah, so this is like a vortice this is a circumpolar vortex. They're not driven that way? Is that what you said?
Yeah, I'm asking. Are they driven the same way as the vortices?
No, in these objects, the exterior flux is like 10 to the 5 times greater than the interior flux. So, no, it's a different parameter regime in your fluids. So it's a bit of a question whether or not in these models it's up for debate whether or not in these models they have seeded them with too much initial vorticity, and so what happens is you get these kind of these features that develop naturally as you'd expect because you're seeding them with too much vorticity. I think that's up to debate, but ultimately, I think that these teach you a lot, but they're 2 dimensions, and these atmospheres are being irradiated, intensely irradiated, only on one side, and so you're gonna get a lot of radial motion, and so this kind of model, it looks you can go obviously to much higher resolution than you can in 2D or in full 3D models, but I'm not sure that it accurately represents what's going on. So the second of 3 ways to approach the hydro is the primitive equations. Now these are 2D Navier-Stokes equations, and then the third dimension, the radial direction, you solve for it, but you assume that it's in hydrostatic equilibrium. So what that means is that vertical velocity can only occur such that it reestablishes hydrostatic equilibrium. So if you have a divergence in 2 dimensions of fluid, then you can have a vertical velocity flow. Now the argument about this is that these are valid when the aspect ratio is high, right? When the radial extent is much smaller than the horizontal extent, which is of course what we're seeing here. So these have been done for quite a while. This was I think the first dynamical models were done by Schoeman and Guillot in 2002, and then there's been several papers by Cooper et al. And Schoeman et al. More recently. And so you can see this is latitude versus longitude. So this is basically the entire surface of the planet folded out. And these are different pressure levels. So this is the highest pressure level, and then this is getting deeper and deeper into the atmosphere. And so you can see there a fairly common feature of this is that you get flow, circumplanetary flow in one direction. And then you can begin to see how this hotspot is advected downwind, as we saw in some of those observations. So finally, whoops. Oh, too much. Come back. There we go. So finally, the other, oh, sorry, one last thing I wanted to point out here. This is the Q here is the radiative forcing term. So we'll come back to that again with the radiation, but that is the way you drive. You represent the impinging flux. So the final way, and the way that I attack this problem, is to solve the full three-dimensional Navier-Stokes equations. We all have seen these before. I don't need to go over them, but continuity, momentum in 3 dimensions, and then this is my radiative term, which is the divergence of the radiative flux, and we'll see how I'll talk a little bit more how to represent the flux. So those again are the dynamics. Let's talk about the radiation. Radiation is extremely important, as we just mentioned. It's radiation's orders of magnitude higher than the interior flux, in contrast to Jupiter, where they're almost equal. So how to treat the radiation? So the other two groups treat it using relaxation methods, and they're formulated somewhat differently, but they amount to basically the same thing. You try to relax the temperature distribution back to some equilibrium temperature distribution on some time scale. Okay, so this is perhaps easiest to understand in this formulation here, where this is your forcing term in your heat equation. So you have some equilibrium temperature distribution that you assume based on some purely radiative models, and you have your actual temperature distribution, and you relax it back on some time scale. And the time scale that many of these groups, the time scale that these guys use is a time scale taken from a paper by Iro et al. From 2005, where they computed this radiative time scale on the adiabat of a giant planet. And so it's a function of pressure, basically. These guys are assuming they're only modeling a single pressure, so they choose a single layer, and they pull out that radiative times constant. More recent. This guy? You just you turn off dynamics, you do a radiative equilibrium model. It kind of falls off like a cosine to the 1/4 or something like that in all directions from the substellar point. And that's your T equilibrium. So. Okay, but so you know the opacity. Yeah. So yeah, you have. Sorry. What? Okay. You have to assume it, and that's you impose this. You have to assume this will come out of a full radiative transfer model that radiative transfer only that assumes opacity and interior flux and things like that. So more recently, this Schoeman 2008 paper has extended this. The problem with this, of course, is only a function of pressure, and this shouldn't be only a function of pressure. So they've extended it to be this is the radiative timescale. That's that tau rad as a function of pressure and temperature. So high pressure down here, low pressure. It's 2000 is high temperature, low temperature, and so these are what they've done here is that they've taken a full radiative transfer model, and then at each point, the perturbed it and actually calculated the radiative time constant. So my approach is somewhat different. It's called Flux-Limited Radiation Diffusion. It was first suggested by Livermore and Pomerang in 1981. And it's essentially a closure relationship for the radiative transfer equations. And in my formulation, I assume that at this point, that in the stuff I'm going to show today, I assume that the radiative temperature is the same as the gas temperature. So that means that this radiative energy, E, the integral of this, will be a t to the fourth, where t is the local temperature. So the way that flux-limited radiation diffusion works is you take this full radiative transfer equation, you assume that it's slowly varying in space and time, and then you define some sort of quantity like this. It's proportional to the gradient and the temperature and the energy density. And then you can basically say the flux is going to be in the direction of r times some sort of parameter. You normalize it properly, and you can derive what this expression is, this flux, and you get the following formulation. And you can actually derive lambdas too, or you can you can derive the functional form of lambda, which is this what's known as the flux limiter. And here I've just plotted an example of what lambda would be. And so you can see that this parameter r, which is inversely proportional to the optical depth. So as things become very optically thick, r goes to 0, and this flux limiter goes to 1/3. You reproduce what you'd expect in a diffusion limit, which is 4/3 times the gradient of temperature. But as you get to very optically thin regions, lambda goes to 0, but this r also diverges, and so the ultimate, the limit of this in the low optical depth region is CE, and this is where the idea of a flux limiter comes in. So the upshot of this is that this way of treating radiation diffusion is accurate in the limits between of optically thin and optically thick, but
The direction is off in the optically thin limit, but it could be, right? Because you could have optically thin radiation transfer glancing in from the side and have the direction of R be pointing in a different direction.
you mean if you have impinging radiation?
For instance.
Yeah, it's a little bit. All the intuition that you build up, I build up about radiation transfer is a little bit odd when you try to apply it to hydro radiation, because in that situation you have impinging radiation coming in this direction and outgoing radiation going this. The net flux is 0, right? But that's not going to be true in a hydro simulation like this, right? So I don't know if this addresses your question, but the net. Later on, I'll talk a little bit about the improvements I'm making on this, but I think what you're trying to get at is the idea of basically a heating term that's coming directly from the stellar irradiation. And I'll try to get into that a little bit in the end. So, no, it's okay, please. So for this, I need opacities, of course. So recently I've incorporated opacities of Friedman et al. So this is the opacity table that I use. This is log of opacity as a function of pressure and temperature. It has some very interesting features. This particular opacity has titanium vanadium oxide, which will become important later on. Okay, so before I get into the results, I just wanted to remind you again try to sum all that up. There are three different types of ways of doing the hydro, and so far 2 different ways of doing the radiation. And so any given model could pick this one and so on and so forth. But what has been done is these 2 together with the relaxation, and then what I've done is try to couple the Navier-Stokes with the flux-limited radiation. Okay, so most of the plots I will show you will be from a synchronously orbiting planet in a 3-day orbit. So the period of the rotation and the period of orbit is 3 days around basically the sun. The hotspots here. This is the photosphere of the planet. This is the anti-solar point facing directly away. It's the hotspots here, and it's stationary. It's not moving because it's synchronously locked. These are all done in a rotating frame. Now you can see right here, unfortunately, I've cut out the poles, and the reason I've done that is because I have a spherical grid, and it goes to 0 up there. And so unfortunately, I do have to cut out the poles in my simulation. Of course, suggestions of some sort of patch on the top, but I haven't gotten to that yet. So this is a map of temperature, and ranging from about 680 degrees from the coldest spots, which are right here, to say 1100 degrees on the hottest spot, which is slightly downwind, about right here. And so you can see two very obvious features. Rotation senses upwards, so this eastward flowing jet is concentrated towards the equator, while as this westward going jets are concentrated in the upper regions here. And so you can see this temperature, this energy is being advected from the day side along the equator, along the eastern terminator, while on the western hemisphere it's happening much more near the poles. The velocity structure maybe shows a little bit more in depth what I mean by this. So you can see these 3 jets, basically. This guy's going eastward, this guy's going, and these guys are going westward. Velocities are quite high, 2.6 kilometers per second. 2.6 kilometers per second. Near this area here, that near the terminators. Now, these are all at the photosphere. So at depth, we can look at what's happening at depth. And so these are 2 slices. They're meant to correspond with the jets. So if I go back here for a minute, what I've done here is I've taken a slice here at the equator and another slice here at higher latitude. So here on the left is the equator slice, and at mid-latitude. So, and these are not to scale. I should say that right off. These are exaggerated immensely to highlight the features. But anyhow, you see your interior, spherically symmetric interior boundary condition, and then you have your radiation coming through here. And as the winds travel around, you can see these tongues of advected energy stretching towards the backside. And then around the other side, you can see a return flow bringing cool material back to the day side. You can see this tongue of cold material. And here is exactly one of the reasons you see these temperature inversions, is that fluid that's going to flow to the backside has to come back. It's cooled by the time it's come back, and it's coming back to the other side, and it's going to cause this inversion. Now, on higher latitudes, the energy is advected around this way a little bit further. You still see some of these cooling flows at depth. And I believe I have next this is maybe easier to see on here. If you look at the pressure temperature profiles in the equator and the mid-latitude again, the various colors, I guess you probably can't see this one here, is 90 degrees, correspond to the solar point, the anti-solar point, and this is the 9-degree east point. So you can see very clearly this temperature inversion occurring both at the equator and at higher latitudes.
So is the indication that when you see temperature inversion, that's evidence for a stronger advection?
Strong wind advection.
Strong wind?
Yeah. Well, it's not. Even in the cases that I'll show some high opacity cases later, where there's not so much, the winds aren't circumplanetary. You still have to. It still comes back and it still cools. The magnitude of this doesn't change that much. I mean, the basic thing is that again you cool as you go back, and that fluid has to return to the front.
But then what does it mean we don't see?
when you don't see the inversion.
Yeah.
Well, the inversion is actually due to two things. And it's unclear which is dominant. The other is an opacity effect. But yes, I mean, this is still something this I think would be the Grail question the Golden Grail question at this point is like how do you distinguish those two? Is that a dynamical effect or is it an opacity effect? The spectral modeling community thinks it's an opacity effect, but it's very clear that you have them from the dynamics. You can see actually you also get this inversion. Again, you can't see this, and I apologize. There's an inversion at the 90-degree level as well, just from this hot material being pulled, advected around to the night side here. So you get an inversion here as well, of a slightly different nature. So, very next slide. This temperature, so this temperature profile, dichotomy, hot, inversion, no inversion, was actually suggested in, I think, 2003 by Hubeny et al., but has recently come to the forefront with these observations. And the explanation that people have put forward so far is it's due to this titanium-vanadium oxide condensate that forms when you're sufficiently hot. And so you have this impinging photons that suddenly see this extra source of opacity, and so you're absorbing all this stellar energy very high up in the atmosphere. And so you would naturally break into two classes of planets, those that are hot enough to form this condensate and those that are too cold to form that condensate. This runs into a bit of a problem when you have an object like 209458 that crosses this line in multiple places, in that there's a phenomena where if you have a condensate where that happens, what will happen is that the condensate will eventually diffuse down into the lower, the lower in depth, it'll diffuse down into the higher pressure regime, and it won't be present up in the high atmosphere. Unless you have some sort of dynamical mixing to bring that back up into the upper atmosphere, you won't see it up there. So it remains an open question, but this is definitely the explanation that's being put forth in a lot of the community. So you can try to figure out whether this is a radiation or a dynamical effect. In this models, which don't include dynamics, these are one-dimensional radiative transfer models. In these models, it comes out as a flux effect. So this is incident flux. So incident stellar flux is a function of mass or as a function of gravity, planetary gravity. And so the claim is all these objects should be the class that has the inversion, and all these objects should have no inversion. So again, this is a very interesting question that we're trying to address eventually here. How am I doing on time? Not very good. Okay, I'll try to hurry up. Jet velocities. These are equator mid-latitude. You can see one's going eastward, one's going westward. The two things to note here. The dots here are the location of the photosphere for the opacity table that I've used. So above the photosphere, you actually get somewhat of a symmetric latitudinal convection way up in the atmosphere. And this is very similar to some of the high opacity simulations. But nevertheless, near a bulk of the energy is transmitted way down here by the photosphere, and all this is traveling in a westward manner. So just quickly, the radial velocity structure. You can see this here again. The photosphere is down here. So all this is significantly above the photosphere. And so this is at the equator. You can see red is counterclockwise here. So this stuff is moving around the equator here. And then in this guy here, we have flow moving in the opposite direction near the photosphere, but up high, you still have this somewhat symmetric latitudinal convection. Yes. So, well, rotation does two things for you. Rotation is what breaks this symmetry and funnel. I mean, it's the Coriolis force that's funneling. This guy's coming to the east and this guy's coming to the west. They're going opposite directions. So this guy is being funneled towards the equator by the Coriolis force, and these guys are being pulled towards the poles. So that's the dominant thing that rotation does for you. Rotation also changes the width of the jets. So if you compare something like that to Jupiter, it's Jupiter has many bands along here, and but this can entirely be due to the rate of rotation. So Jupiter is rotating once every 10 hours. These guys are 3 days and 1 day. So if you calculate what a characteristic number for this kind of a flow, which is the Rossby deformation radius, which basically tells you the scale of jets and bands. You can see that the omega is is much different for these objects. So sorry, for Jupiter, the deformation radius is much smaller than its radius, while as due to increased scale heights and decreased rotation rates, the deformation radius for these objects is much larger. So it's on the order of, that's meant to be on the order of symbol. It's on the order of the planetary radius. So you can only get a few jets. And this is behavior that I see and I also see in the primitive equation models as well. Slightly. Not much, though. It's this is the scale here is like 700 to 1100, and this is it's several hundred centimeters per second faster. So this is 900 centimeters to. Oh, sorry, this is temperature. What am I talking about? Next. I knew it didn't change very much. There it is. Is that velocity? Yes. There's velocity, and they're on the same scale. So you can see that the absolute velocity doesn't change by much. So, that's what is that? 2 kilometers a second right here, and so it's slightly faster in the fast rotation, but not considerably. The other thing you can see, which is not, I still don't understand this. I must be honest, I don't understand this. Is the depth or the vertical extent, the radial extent of the jet is slightly larger for the faster rotation. So this is something left to be explored.
Sorry, did you put any explicit dissipation?
No.
To the fluid?
No.
Nothing.
Yeah.
Very spread.
Yes, and there's
Based on that answer can be converted.
into viscous heating. Yeah, sure.
So you don't have it.
I don't have it, and it may play a big role. There's, especially on this next guy here, in models like this, I'll explain this in a second, but this is a model with higher opacities where you have much clearer, I'll just skip ahead here, it's easier to explain. Here's the velocity structure for these type of things. So you have these two, very, very much different than this situation. So you have these two intersecting flows, basically, at these stagnation points here. And you're going to be having flows diving underneath each other and baryoclinic instabilities and all kinds of interesting things occurring. So, sorry to jump ahead here. Okay, so if you vary the opacities, you might expect different things, and indeed you get them. These are the opacities that I've been using. These are pretty much the current, what people believe giant planet atmospheres are. They've been used to fit to model in spectral models and such. That's the top plot, and the bottom plot here, as I mentioned, is much higher opacities. They're actually using interstellar opacities. I use these because I did this model a while ago, and this is what was available to me. But they're a factor of about 100 difference between the two opacities. So you can see, this is a plot of temperature. The blue down here is, down to 200, 300 degrees here. while on the back here, the blue here is on the order of 700 degrees. So you get a much larger temperature difference for the high opacity case than for the low opacity case. And it's pretty easy to understand. The energy advected to the back side, the temperature on the back side is going to be determined by a competition between the cooling of the material as it travels to the backside and the rate at which it goes, the time scale at which it goes backside. So if you write down a cooling time scale and a crossing time scale, and you say, okay, well, they're going to be somewhat equal because if one exceeds the other, they're going to try to balance each other back out. If you write those two down, then you can come out with an expression, an approximate expression for the nighttime temperature, which is inversely proportional to opacity. So the higher the opacity, the colder the night side. Now this is, I'll leave it at that. Okay, so to the velocity structure, I've already shown this, but again, here you can see much more clearly that that structure I was talking about, influenced by the Coriolis force. So the material moving from the subsolar point across the terminator falls down this huge temperature gradient, accelerates to supersonic velocities, but it's funneled to the equator here and then pushed towards the poles here. So it's just. It's what's called a modified Van Leer advection scheme, and has been used for various shocked situations in the past. And I haven't dwelled too closely on that aspect because I think these are unrealistically high opacities, but in principle it can handle those shocks. So I wanted to come back just for a second here to this advected hotspot. Here, so what I've done is I've just basically calculated what you would see as a phase curve if you looked at these objects that I've simulated so far. There's a whole list of things here, perhaps too busy of a plot, but these points here are the minima of the curve. And so you can see they're all shifted away from, other than this very high opacity case, they're all shifted eastward of the anti-solar point. And then this would be your subsolar point. And again, they're all shifted eastward or downwind of this subsolar point. Again, to highlight the confusing claim made by these authors that the coldest spot was in the same hemisphere as the hot spot, it would mean that the coldest spot is actually over here in these plots, which is quite difficult to do, in my opinion. But it may be something that we have to still struggle with. I wanted to very briefly return to this inversion aspect again, and what's causing this inversion. So these are recent models of the observations of 209458 that include the effect of an inversion, that fit to an inversion. And so these are the spectra of various models. And then these would be the pressure-temperature profiles, corresponding pressure-temperature profiles. And so what they've done is they've done two things with these models. These are radiation, obviously, they're radiation, wavelength-dependent radiation models. So they've tried to parameterize the redistribution. And the way they've done that is they've taken energy at depth away from the day side and injected it onto the night side. And of course, this is entirely ad hoc, but they try to vary that to some extent and see what happens. And then the second thing they've done is they've included an extra unknown source of opacity. So I mentioned to you that this titanium vanadium oxide compound is not expected to be high in the atmosphere. It's expected to all be at high pressures, much deeper than observed. So there's some source of opacity high in the atmosphere that's causing this inversion. And it could be some sort of dynamical mixing upwards of the titanium vanadium, but for this moment they included it as an unknown parameter. So here again is what an inversion would look like in these models. The previous inversion models I showed you only really calculated up to a pressure They didn't include this area up here, which is why they just kept going up and they never turned over. But here you can see, so for example, comparing these three models here. So this PN factor is the degree of redistribution. So if you can compare the purple, red, and green models, that's these three here.
We have a course starting now.
Okay. All right. Okay. Well, the point is redistribution, both redistribution and opacity play an effect on creating this inversion. So I guess yeah. So I'll skip to the end. So anyway, to conclude, these planets, we're starting to get enough observations to suggest they're a very diverse class of objects. All kinds of things we're seeing, properties, rotation, irradiation, opacity, perhaps more things will all play a role in shaping this diversity. But it's unclear whether or not this is enough to explain that diversity in the observation. I didn't get a chance to go into it, but this I'm currently implementing a new way of treating radiation transfer. It's perhaps more correct, and hopefully that will be things like the inversion will pop out a little bit more clearly. And then, of course, keep your eye on these observations. I hear there are a lot of observations being worked on right now that haven't been published. So I think we're going to see a lot of these type of things come out in the next year. So, thanks.